So, good morning, everyone. My name is Qizheng Yang, and I'm a PhD student from UMass Amherst. So, it's an honor to be here today to present our work, DiffServe, efficiently serving text-to-image diffusion model with query-aware model scaling. So, this is a joint work with my collaborators from UMass and Adobe Research. So, let's start with a quick overview of how a text-to-image diffusion model works. So a user provides a prompt, in this case something like generate an image of a cat. And this prompt is sent as a query to a diffusion model server. What happens inside this model is a process called denoising. And the model starts from pure noise and over many steps gradually refines the noise into a realistic images that match the input prompt. The diffusion process can involve anywhere from a few to 50 steps depending on the model. And once the final image is generated, it is sent back to the user. While the result can be very impressive, the multi-step iterative result process is computationally expensive and is a key contributor to the serving cost of diffusion model. And there are many diffusion models available today, and they offer different trade-offs between image quality and generation time. As we move to the right along this curve, model gets better at generating high-quality images, but they also become slower and more expensive to run. And on the other hand, faster models like SD Turbo or SDXS generate results quickly, but may compromise on quality. So the natural question is, can we actually leverage this trade-off when serving diffusion models? And instead of committing to one model for all queries, what if we could dynamically choose the best model for each individual query, given workload changes and resource availability? Now, one key observation is not all queries are equally hard, and this finding motivates our project. For example, a prompt like generate an image of the downtown of a city is fairly complex. And if we use a lightweight model here, the result is unrealistic. But a heavy model can capture the details pretty well. So this kind of queries are considered hard query, which requires more capacity to maintain quality. On the other hand, simple prompts like generate an image of a cat and can be handled well even by a lightweight model. And in fact, the real difference is minimum. And they are considered as easy query. And in our experiments, we observed that 20 to 40% of the queries are easy queries, for which the lightweight model will generate images with comparable or even better quality than the heavyweight ones. So using them smartly can greatly improve the efficiency without hurting the response quality. So this brings us to our core idea. We propose query-aware model scaling, a system that dynamically selects the right model per query based on its difficulty. So instead of picking a model ahead of time, we use model cascading to adaptively select the model for each individual query. So let's see how it works. Let's say we have queries from users, and every query firstly goes through a lightweight diffusion model. And then we add a discriminator that evaluates the image output from the lightweight model and estimates its output. The discriminator outputs a confidence score, essentially how likely the image is good enough, by comparing with a threshold. If that score is higher than the threshold, we return the result right away, and this saves time and GPU cycles. And if the discriminator is not confident, we reroute the query to heavyweight diffusion model. And the second stage model generates a higher quality image, which we then return. And in this way, we only use heavyweight model when truly necessary, achieving both quality and efficiency. One of the key challenges in our system is designing a good discriminator, a model that decides whether the output from a lightweight model is good enough. But this is non-trivial. especially for generative diffusion model, where output can vary in subtle ways. And to address this, we train the discriminator using a real versus fake declassification objective, where it learns to distinguish real and generated images. So why this is a challenge? Here's a plot that shows image quality varies with latency under different routing behavior. And the x-axis shows average latency of all queries, and y-axis shows FID score to represent response quality, where lower values indicate better response quality. And the blue curve represents a random routing strategy. Then we can see that existing perception metrics like clip score or peak score perform even worse than the random. They introduce additional computational overhead, and they fail to distinguish hard and easy queries. And instead, in our solution, we train a binary classifier to distinguish real images from the generated ones. And we use high-quality real image as positive samples and output from both lightweight and heavyweight models as negative samples. Then during inference, the discriminator no longer needs real images. It simply evaluates output from diffusion models and produces a confidence score, estimating how realistic the image looks and guiding whether to reroute in the cascading pipeline. When we compare our discriminator with other baselines, our discriminator, which is a red curve, consistently performs better. And this means it routes more effectively, efficiently, and with better control of quality. The second challenge is that the confidence threshold always interacts with other system-level parameters, which should be co-optimized instead of tuned independently. And we address this by designing a mixed integer linear programming-based resource allocator to find the optimal configurations. And there are multiple resource allocation parameters we need to co-optimize, like confidence threshold, number of workers for lightweight and heavyweight models, and batch size, etc. So this will result in a very large design space as shown in this figure. Each point in this figure is a configuration with different serving throughput and response quality. So in our solution, the MLP-based resource allocator helps us search for the printable frontier, which are the red dots. And this gives you the optimal response quality given a serving throughput while meeting system constraints like latency deadlines. And this let us find the optimal configuration under varying workloads. We implemented a framework, Diffserve, for query-aware model scaling. Here's how it works. So a client will send queries to the load balancer, and the load balancer routes them to workers with lightweight diffusion models and discriminator. And the discriminator estimates the result quality. If the confidence score is high, the result is returned directly. And if not, the query is rerouted to a heavyweight model for a better output. Meanwhile, workers send status updates to the controller, and controller use the information to make resource allocation decision and loads the right model from the repository. It then updates the load balancer so that queries can be routed to appropriate workers. And this is a control path and data path of the Diffserve. Before diving into performance, let's quickly walk through our evaluation setup. We use text prompt from the MLSys COCO dataset and set an SLO of 5 seconds for each query. And in the model cascade we used, the lightweight model is SD Turbo, running on an V100 GPU with just 0.1 second latency. And the heavyweight model is SD with 1.5, which has a latency of 1.8 seconds. The next is the baseline that Diffserve compares with, as shown in this table. So the first two, the Clipper Light and Clipper Heavy, use fixed model for all queries and is not query aware. And Proteus is the state of the art. It introduced dynamic resource allocation, but it routes queries randomly to each model variant, so it's not query aware. And our method, diffserve, combines both query awareness and dynamic allocation. For evaluation, we use two key metrics. FID, where lower values indicates better response quality, and the SLO violation ratio, which measure how often responses miss their deadline. So let's first look at how different systems perform under medium workload. So this figure has SLO violation ratio on the x-axis and FID on the y-axis. So static baseline like Clipper Light and Clipper Heavy struggle, as shown in this figure. Clipper Light meets SLOs but with poor quality, and Clipper Heavy gives better response quality but violates SLO heavily. And now Protest offers a middle ground performance between two Clipper extremes by tuning the model variants based on demands. But it still offers suboptimal performance since it routes queries randomly instead of considering query level optimization. And this is where diffserve comes in. Diffserve consistently stays in the bottom left corner, achieving both low quality FID and SLO violation simultaneously. We attribute this to the query-aware nature of diffserve, as it can select the appropriate model for each query based on its content and difficulty. And this advantage holds across different workloads. The figure shows the performance comparison under low load and high load. And we can see that diffserve maintains the best trade-off under various workloads. And this shows that diffserve is adaptive to workloads change by dynamically changing the confidence threshold and allocating resource for each worker. And we have more experiments on real-world traces in the paper, and please check the paper if you are interested. So to summarize, we propose diffserve, which optimizes efficiency and quality of text-to-image model diffusion model serving by leveraging query-aware dynamic model scaling. And we conducted experiments which show that diffserve can improve image quality by up to 24% and reduce the latency violation by 19 to 70%. And finally, we implement the diffserve framework, and the source code is available on GitHub. Here's a QR code for the repository. And that's so much for my presentation, and thank you all for listening, and I'm happy to take any questions.
All right. Thanks so much. So our next talk will be lean attention. So if you're the speaker for that, please come up and set up. Meanwhile, we have time for a few questions. I'll start off with just one. So a lot of diffusion models you see, there's the kind of the big version, and then there's a distilled version like FluxDev versus FluxChanel. How does something like that, when you have two versions of the same model, integrate into your system?
Can you repeat the first few?
So when you have a step distilled model, so a model that can generate high quality images but with fewer steps, for example, in the Flux family of models, how does that integrate into your system?
Yeah, that's a good question. Like if you have a good quality, if you have a model that can generate image with like a few steps, but actually nowadays people still preferring like using more steps to generate a higher quality. So you can use like a model with fewer steps as a lightweight model, and the same model with more steps as a heavyweight model. So it can also like provide a trade-off between latency and quality.
Thanks so much. Any other questions from the audience? I see one in the back.
Hi, thank you for your work. You mentioned at the start that 20 to 40% of the queries were easy queries. How did you measure that, and why did you not use that for like choosing to run the lightweight model or the heavyweight model instead of running the lightweight model every single time?
Yeah, that's a good question. Like to evaluate to like classify easy query and hard query in the motivation, we use like some metrics, the existing metrics like peak score. And we just compare, like, given a prompt, when we generate the image with lightweight model and heavyweight model, we get output, and we compare this output to see, like, if the score are similar. If it's similar, then it's easy query, and if not, then it's not easy query. And actually, so for your second question, do you mean like we can design like router before putting the prompt into this cascading pipeline? Yeah, that's also a good question. But yeah, it's an open question to like estimate output of image just given the text prompt, and because like image can be vary depending on what model you used and like the complex of query. So it's kind of hard. We did some experiments, but it didn't work well in our like paper. So we use cascade pipeline. Thank you.